we're now in a position where we can start to put together these elementary transfer matrices to see the process for some elementary cases anyway. And the first one I'm going to do is a pretty standard one, is find the optical system matrix for the thick lens. And here I've got a thick lens. It's in air, so N1 and N2 are both 1. The index of refraction of the glass that the lens is made out of is 1.6 in this case. R1 is in our system is convex, so that's a positive value R. This one is R2 is convex. R1 has a magnitude radius 45 centimeters and R2 30 centimeters. And the thickness of the lens, and that's the vertex is 5 centimeters. And what we'd like to do is we would like to get the transfer matrix that takes you from this input plane, which is right there through the first vertex, and the exit plane or the output plane. So input and output plane, or entry and exit the planes. I see both the terminology. And so generally you always specify these, and I draw them on the figures when I'm doing them with dashed lines, so that I know precisely where I'm entering and leaving from. And now then, you can go to that corrected table 18-1 in your textbook, and to develop the matrix that describes this whole thick lens system here, this optical system. And again, remember, the way you do it is you approach it from left to right, but you write the matrices from right to left. So the first matrix I'm going to write here is the one that I'm going to call the refraction at R1, R1, and then to go from here to here to the other one, I have to do a translation by the thickness T, and then finally, so that's here, so I write that one next, and then I go through the surface R2 to get to the output. And so the very last thing I do from my input to my output is the order, shows me the order. So the very last thing I do should be this one here. So I go when I write them from left to right, but I've written these. When I wrote this down, I wrote R1, T, R2 in the reverse order. And we just go to that table. This is the way I like to write them, so let me write the general formula. Uh, one, the refraction at a spherical interface is 1, 0. I like to put a negative sign, N2 minus N1 over N2R and N1 over N2. The reason for that, this is the final, and that's the initial over final, and this is initial over final. No, that's just the way I remembered them. And in our case, we've got all of those. The final through that first surface, if you look up here, through here, the final is 1.6. So N2 in that case is 1.6. I started off in air, so it's mine N1 is 1. N2 was 1.6, and then the radius of curvature of that first surface was 45 centimeters. 0. And then here I have the initial, which was 1, over the final, which was the glass, which is 1.6. So I get 1, 0. When I multiplied these out, and sometimes it's easier to keep them in fractions, and sometimes it isn't. So I've done these all sorts of ways, but in this one I actually am going to get 0.6 over 1.6 times 45, but then when I divide 0.6 into that, I get 120. And I left off, this should be 45 centimeters, but this is reciprocal centimeters. And then I'll just leave this as 1 over 1.6. remember the translation. So here I'm going, I've gotten through the surface, and now I'm going to go from here to here inside the media. And as a result, my translation through this distance d, well, that's just the thickness of the thick lens, and 1d. So here it becomes t, 0, 1, and the thickness from above was given was 1.5 or was 5 centimeters. Sorry. So my translation matrix is this. And then finally I have to go through, I'm on this side, on the side where N1 is 1.6, and I go over to N2, which is 1, to get just outside. And that's my R2. And again, I generally write this in this form every time. This is final minus initial. Well, the final was actually 1. The initial was 1.6 here. The initial or the final is 1. I wound up on the air side, and then the radius of curvature was 30. Is that right? Yeah, 30. R2 was 30 centimeters. Notice both of these radii are, if you look at these by our sign convention, these are both positive values. So I'm really putting these in with the respective sign. In this case, they're both positive. N1, well, I started on the glass side. That's so N1 is 1.6, and then I finally get outside to air. And then I rearrange these a little bit. The first two don't need anything. 1 minus 1.6 is minus 0.6, but a minus makes that a plus over 1 times 30, and 0, 1.6, 1.6 over 1. And then I divided 0.6 into 30 to get 50, so this is the same as 1 over 50 and 1.6. And now it's really just a question of multiplying all of those three matrices together. So I put in R1, so refraction at the first spherical interface, the translation through the thickness, and then the refraction at the second interface. And if you just do matrix multiplication, I'll let you check these. I tried to fill in as many details as possible. So this will be 1, and this will be 5 times 1 over 120. This will be 0. This will be 5 times 1 over 1.6, and so on. So multiply all that out. I usually have to do it 5 or 6 times because I usually screw up. But I'm sure you guys are much more adept at this sort of stuff. It makes you appreciate something like MATLAB or something and multiplying these matrices together. And you can use those for homework. It's easy. But ultimately, you're going to need to be able to multiply 2 by 2 matrices. If you don't know how to do those just yet. Need to go and review that. Final, after some simplification, I come down to this and multiplied this out, and then I reduced it somewhat to finally get M in sort of the final form here. Notice a couple of things about and these are good checks for you. If you carry units along, the 2 diagonal terms are always dimensionless. So those are dimensionless. The one in this corner will always have units of length, and the one in this corner will always have units of reciprocal length. So this one's centimeters, reciprocal centimeters. Another thing to note is if I take all of those translation matrices, they all are the index of refraction I started in divided by the index of refraction I ended in. And that holds in general. If I have a product of matrices, So M is the product of R1 times T times R2. But the determinant of a product is you just take the determinant of each one of the individual matrices and multiply them out. And R2, the final was N, the initial was 1. The initial N was 1. Translation was 1.6, and the final was 1.6, so that becomes 1. And then the first one, the initial one was 1, and the final was N, which was the 1.6. And if you look at that, that's product is equal to 1. In fact, the determinant of the optical transfer matrices, these elementary optical transfer matrices, and their products ultimately has to be 1. And so this is a good way to check. For us, our matrix is here. So if I take the determinant of this matrix and it's not equal to 1, then I know I've made a mistake somewhere along the way. It doesn't mean that just because it is, I'm guaranteed that I didn't make a mistake. I could have had 2 mistakes that cancel each other out in this determinant. But the nice thing about it is if you look at this, the determinant of it, this one times this one minus this one times this one, is dimensionless. So the determinant of the transfer matrix is always dimensionless. That's another good check as well. So let's do that for that one. It's going to be 23 over 24 times 17/16 minus 7 over 1200 times 25/8. And I did that here someplace. Here. Notice it cancels out, so everything is dimensionless. When I calculated these, I got 1.018229. And when I calculated these, I got 0.018229. And so when I subtracted, I got 1. And so I have some assurance that my final transfer matrix is here is it's in good form. Usually, after I've checked things, I would turn all of these into a decimal form, but I won't do that here. So, typical kind of calculation in this matrix form.